So we're going to look at something which is a little bit of a lost art, and that's going to be constructions. So constructions are going to be actually building things and then comparing them by hand instead of just taking a theorem at face value. We're going to look specifically at constructions that are going to be related to side, 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 angle, side, and hypotenuse, leg congruence properties. We'll look at isosceles triangles, altitudes, and circles. So the idea of congruence and similarity is that if two things are congruent, I should be able to reconstruct it and measure it, and they should have the same measurements. So here I have congruent fish and congruent birds have the same shape and same size. Here I have similar triangles because they're going to be the exact same size, but they do have the same shape and they have a scale factor. So two similar objects have the same shape, but not necessarily the same size. If it's congruent, it has to have the same shape and the same size. Congruent objects are considered similar, but similar objects are not considered congruent. So the definition here is just some notation that we use that two segments are going to be congruent if and only if they equal one another, and two angles are going to be congruent if and only if the measure of the angle is the same. In a geometric construction, this is again by hand constructing these shapes. Given 2 points, a straight line can be drawn between them, and that's going to be a unique segment that's going to connect those 2 points. Then I can take those 2 points and a circle can be drawn if I'm given a center and a radius. So if one endpoint is the center and one endpoint is the radius, I can go ahead and construct that circle around it. Any number of points can be chosen on a given line, segment, or circle because there's lots of different points that exist. Points of intersection for two lines, two circles, or a line and a circle can be used to construct segments, lines, or circles. And you're going to see why we're talking about circles when we get a little further into the construction idea. No other instruments, such as a ruler, triangle, or protractor, or procedures can be used to do a construction. So a lot of times students will say, I'm going to construct a square by using my ruler. No, you're going to use a compass, and a compass is going to act as the protractor, and you're going to use a straight edge, which is going to be how you connect the dots. So constructing a circle, if we're given its radius, is going to follow this basic process. So I'm going to take my compass, I'm going to measure that radius, and then I'm going to put it in the center and drag it around in a circle to construct that compass piece. Here, if I'm constructing segments, there are many ways to draw a segment that's congruent to another one, but remember, we're not using some of those tools. So if I use a ruler, that's probably what most students are going to say. They're going to use a ruler, trace the segment, and use the method below. But what we want them to use is a straight edge and a compass. So if I measure that, the width of that line segment with my compass, I can then find a congruent line segment on my line by just moving my compass down to my line. Triangle congruence is going to happen when all things align and all angles and all sides are going to be congruent. Congruent triangles are shown utilizing this notation for congruence. And if the two triangles are congruent, then the corresponding angles and sides have to also be congruent. And that is from the theorem, corresponding parts of congruent triangles, so CPCTC, are congruent. So corresponding parts of corresponding triangles, corresponding parts of congruent triangles are congruent. Sorry, we got it there. So these are some examples, and if we wanted to write the appropriate notation for congruence for each pair, then triangle ABC would be equal to triangle EFD. Now notice the orientation of these. If I do ABC, that has to be the same pattern as EFD. It's not because it's going to just be the top starting point. I have to make sure that that right angle and that 3 correspond to the right process in naming the triangle. In part B, ABC is going to be similar to RQP, or congruent to RQP. And if you're looking at that, if this is 30 degrees, then this is 60 degrees. So since A started off with 60, I have to start off with R here. And then it went from the 60-degree angle to the 30-degree angle here. So that's why it's RQP. There are some shortcuts to doing congruent. So to know that two things are going to congruent, you're going to check all sides and all angles. But we can shortcut this process by just finding out if three sides are congruent. So if I'm using side, side, side to explain why the given triangles are congruent, I'm going to look at the measurement. So I need three sides that are equal in this triangle. And if the three sides are equal, then I know the angles are also going to be equal. So this would be the geometric explanation for both. If I'm going to construct the triangle given the three sides, first I'm going to start off with constructing that line segment by measuring it with my compass. Then I'm going to locate the vertex of B by drawing the arc with one endpoint on A and one endpoint by C. So it gives me these two circles whose radiuses are going to be congruent to those AB and BC. So I'm measuring AB, I'm drawing an arc at the end of A, I'm measuring BC, and I'm drawing an arc at the end of C. Now, those circles are going to intersect, and that point where they intersect is going to be point B. Then I'm going to use a straight edge to go ahead and connect the dots. So again, this is an area that unfortunately has fallen by the wayside when we're really working with students on this. And it's something that I strongly encourage you even to just do yourself on the board so students can see what the theorem is actually saying. The triangle inequality says the sum of the measures of any two sides of a triangle must be greater than the measure of a third side, otherwise we're not going to be able to connect our segments. Now, if I want to look at constructing congruent angles, these would be the actual construction steps with the compass. So using a compass and straight edge, it is possible to construct congruent angles. We don't have to use a protractor, which is kind of the default mode a lot of students go into. Another congruence theorem is side angle side. So if I have two sides that are congruent and the angle between them, it has to be between them, then I can say that all six pieces are going to be congruent. If I'm constructing something that involves two sides and an included angle, I can do that with my straight edge and my compass. So here's an example of side angle side to show that two pairs are congruent. So notice how that 70 degrees is between the two known sides. It has to be between the two known sides, otherwise you cannot use the congruence statement. Here in the second one, we know that they share that middle side there, and we know if they're parallel that they have alternate interior angles that are going to be congruent. For the hypotenuse leg theorem, that tells us if we have a right triangle and we have two congruent hypotenuses and one congruent leg, that we can then say that the two triangles are congruent. If I'm looking at some of the selected properties, any point that is equidistant from the endpoint of a segment can be a perpendicular bisector of the segment. So these are just some generalizations. Any point on the perpendicular bisector of a segment is equidistant from the endpoints of the segment. If I'm looking at selected triangle properties, for every isosceles triangle, the angle opposite of the congruent sides is congruent. Those are considered to be the two base angles, and they are going to have the same measure. If I have the altitude of a triangle, which a lot of times we call the height of a triangle, and it's a perpendicular segment from a vertex to the line containing the opposite side of the triangle, then the three altitudes in the triangle are going to intersect at one point. This is another construction piece where we look at constructing that perpendicular bisector. Where you see the blue lines are where the arcs are going to intersect from the construction utilizing the protractor. You can also find a lot of videos on this online that are extremely helpful to help you with designing these. If I want to construct a circle that's circumcised about a triangle, I have an interesting point here called the circumcenter, which is where all of the angle bisectors or the vertexes of the triangle are going to meet. If a circle can be circumscribed about a quadrilateral, the sum of the measures of a pair of opposite angles in a quadrilateral is 180 degrees. So that means that the opposite angles are going to be supplementary. Conversely, we can also prove that backwards, which is what a converse does.